Hello and welcome to ABB TechTalks webinar, Best Practices for Icebreaking Ship Design and Operations. My name is Samuli Hänninen from ABB Marine and Ports, and I will be the moderator in today's webinar. ABB Azipod-propulsion technology elevates icebreaking capability and performance of a vessel to completely new level. This webinar will lead you through the different icebreaking vessel design and most suitable propulsion alternatives. We will also give you a further insight of best ship operation practices in ice-covered seas. Today's Tech Talk session, presented by experts from ABB and Wilkman Arctic Advisor, will cover the following topics: recent development of Arctic vessel design, best ice operation practices with Azipod propulsion, and latest advancement of icebreaking ship propulsion solution. And at the end of the webinar, we will have a Q&A session. Some practicalities before we get started. Please note that this webinar is being recorded and you will be able to access the recording within the next few days. A Q&A session will follow the presentations. If you would like to ask our speakers a question during the presentations, please click on the chat icon at the bottom of the screen and type the question in the chat panel that will open on the right-hand side. We will address as many questions as we can during the Q&A session. Today's speakers are Mr. Göran Wilkman from Wilkman Arctic Advisor. Göran is currently an independent consultant with extensive experience related to R&D of icebreakers and icebreaking ships, including ice model test and full-scale ship testing in real ice conditions. Mr. Sampo Viheriälehto, Master Mariner, and Sampo currently works as a sales manager for ABB Marine and Ports. Sampo has wide experience in icebreaking operations with both conventional and Azimuth propulsion icebreakers, and he has special knowledge on ice management and offshore operations around the world. And myself, Samuli Hänninen, I work as a key account director in ABB Marine and Ports. I have the responsibility for icebreaking vessels in ABB Global Sales Team, and I have a knowledge and some expertise in bodied electric propulsion for icebreakers. With that introduction, let's get started, and Göran, over to you. Göran, can you please unmute?
Yep, I'm unmuted. So I will not really talk about too much about the development of recent things, but more like an approach to how the project will start and how to continue. And I'm not going to go to any technical details. This is what we try to avoid when we are in the Arctic or any icebreaking thing happening. This is an old icebreaker, Polaris icebreaker, Kiev, that was built in the 60s, and after first season in the Arctic, mainly summer season, it came back to Finland, to Helsinki shipyard, looking like this, and they said that we have some minor vibration on board, and they lost several blades, and that time we didn't really have any computer-aided things to design anything. It was more like, okay, trial and error. So they made the blade stronger, and a year after the ship came back, and now we have one, and reported that now we have one propeller completely silent. So they had lost the whole propellers, and the shaft has broken. ever since we have come a long way to all these computerized things and all that, and that means that today we can avoid this type of incidents. There are all kinds of ice conditions in the north and in the east and even in the south. Here we have heavy ridges and ice mountain in the Sakhalin area, and also big ice fields moving around. On the right corner, we have some ice condition in the Russian River, and in the right lower corner we have a channel leading to town of Dudinka in the Yenisei River in the north that has a winter is about 8 months long. And also we are suffering from darkness, some icing, and all that kind of things give us trouble in sailing in those let's say so hostile areas. I myself have been involved in forever, starting with the model testing in Wärtsilä icebreaking model basing and going through different consultancy things around in Wärtsilä company, and also talking about sales and marketing and running labs and all that. And now I have been 8 years already doing some small consultancy and writing papers, and also that is missing here. I have been writing some books about my life and experience. We have a lot of different projects. We have transport systems from A to B. That was basically in the past that we did a lot of that kind of work, that we have a local icebreaking, harbors, etc., escort icebreaking, assisting ships, cargo transport without icebreaker assistance. That is fairly new thing and has been basically come along with also azimuthing thrusters. And also we have offshore operations, supply, ice management, standby, etc. That means also we have then environment protection, oil spill hazards, and all kinds of problems that may occur. And today we have a lot of research activities, and the climate is changing, and people need to do all kind of that studies in the ice conditions and see how the environment is changing. And also when climate is warming up, the more tourists want to go to icy areas, and now all these kind of things have been really damaged by this virus that is rolling around us today. Development in icebreakers have been basically happening in certain steps, and I'm starting from the 50s, because before that it was more or less really trial and error. And in the 50s we were looking for how they are dimensioned, the hull, and how the propulsion works. And in the 60s we had the real first Arctic icebreakers that were really intended not just make something stronger. I started to look at the hull strength and propulsion, and also looking at materials, equipment for low temperatures. And in the 70s, then we basically had already in place systematic R&D, model testing in ice, and also started to make first optimized special duty icebreakers, improved hull forms, more efficient propulsion systems, and also optimized hull strength. And also there were first purpose-built cargo ships for ice. And then next decade, we were looking for more like economy, improved efficiency, low friction solutions, lower number of crew, because crew is fairly expensive on board, I think, or at least Sipono thinks that. And in the 1990s, we had multi-purpose vessels, like when we had Azipodpropulsion for Baltic summer activity. In also icebreakers were doing some activity in offshore business, and also we had to take care of the waves, how the ship is traditional icebreakers were kind of they were really difficult in waves, and nobody can stand stand that kind of action that was rolling in the ships. And we had also looking for better efficiency and larger ships. And that time also we developed a double acting concept where also ships started to go and break ice running astern so that the bow could be designed for more open water friendly. And in 2000 started, then we were more like looking for the year-round cargo transport in the Arctic and also looking for Azipodpropulsion for the Arctic. A design project, we need to understand the conditions, and also it's very important to see what kind of ships there has been before, what kind of fleet there has been, if any, and also environmental challenges, technical challenges, economic challenges. And what is missing here, we might have also political challenges, who knows? And now the world is at the moment turning upside down in many cases. And we have to think about what's the total mission of the vessel. That is it operating part-time in the Arctic, part-time non-Arctic, and whatever. And also we are talking about safety issues, because that's we are always far away, and safety is vital. And there you have to kind of make a design basis to what are these parameters that we can continue. And here are some pictures of ice conditions around different sea areas, and every sea area is a little bit different. So if you do make one design for one, the other sea area might be completely different. And ice is also somewhat different depending on salinity of water and depending on currents and wave actions and climate in general. In ships, we have already talked about mission, and there is always a client, and there has always been kind of ships that have been built, perhaps for that. And also there we have all kinds of regulations and codes, and also new technologies come along, and we have always infrastructure and the area. The picture behind these words is in the Kara Sea, where a channel behind the ship closed in 15 minutes, and we were trapped. We have, of course, all kinds of machinery alternatives today. Here we have the traditional thing, but I would kind of put there one more, just a fully electric. That is kind of something that we don't really see in a faraway operation, but at least coastal area that could be possible, and it is possible. And we have a lot of different fuel alternatives. All the fossil fuels are a little bit kind of banned today, and we are looking for more electricity and cleaner LNG or hydrogen or whatever might be. If you look at the hull forms, we have a special bow shapes or bow shapes that has been used during the last over 100 years. Most of the thing is the one conventional bow, but then we have all at the bottom we have a cylindrical or conical bows, and everything between that. And everybody kind of people normally fall in love with their own design, so it's typical in the business. Icebreaker propulsion has been developing starting from basically in the subarctic, or we could say here Baltic icebreakers. We had one propeller, one rudder, and then we moved on adding propellers, first two, and then one at the bow, two at the bow, two rudders, four propellers, two rudders, CP propellers, and then two rudders and two up propellers without bow propellers. In the Arctic, the traditional thing has been always kind of three propellers and one rudder, and then there has been a case where you have also controllable pitch propellers. In rivers and lake areas where we have a very shallow water, we have had a problem with putting all the power into the water, so it means either several propellers and rudders, and this means that these kind of ships don't go astern very well. All the others are more or less capable of, and then all this led in the 90s as we had Azimuth propulsion. I have to say that in the mid 80s we couldn't do any conventional geared Azimuth propulsion because the manufacturers say that they can't make that kind of pinions without problems. And then came Azipod, and in the 90s we have already then mechanical drives also for Azimuth propulsion. But we all of them have limits. And this means that we had developing from 2 propellers, 3 propellers, and then today we have 2 in the aft and 1 or 2 in the bow. So we are back to basically the things that we started with, but the configuration is completely different. And then today, when we want to make a kind of a, I would not say safe things, but we have also hybrid propulsion, that we have conventional shaft lines and azimuthing thrusters together, 3 or different number of propellers. In the tanker side, there was a long time when we had only basically fixed pitch propeller and 1 rudder, and that was the kind of some ice strengthening. And then came in the 70s controllable pitch propeller and rudder, and still we were kind of far away from really independent operation. And then we got into the single pod fixed pitch propeller, and then came 2 pods and 3 pods, and then we turned the ship around when we found out that the ships are going actually better running astern. So now we can, on some of the ships, they can do both running ahead, running astern, and then it's subject to the ice conditions. How do you do it? And this running astern, that normally means heavy ice conditions. We have, of course, different kind of operational requirements, and that means ice conditions and open water and maneuverability and also independency. Economics, depending how you want to go around the world or straight, and then it's subject to what you are carrying, and the different industries have different effect on this. Feasibility, nobody wants to go there and build a ship that doesn't make any money. So we have to have a kind of conception design that we are talking about, thinking of how many ships we need and what are the design criteria for different elements, economics, performance, and environmental impact. Environmental impact is getting more and more important today. And also when we make a design, we have to think about the materials, what we have available, the type, what are the local or international rules, type of ships, structure. Also building technique, where to be built. Not every shipyard can build possibly the ship that we want to have. Transit simulations are today one tool that you put kind of ice conditions in the computer format, and then you calculate performance in ridges and level ice, and then you get the speed along a certain route. And one example of that was done. This was done already over some 20 years ago. We were simulating oil transfer from Petsora Sea to Rotterdam, or Petsora Sea to Murmansk and Rotterdam. We had 3 different sizes of tankers, and half of them were simulated so that we had tanker with icebreaker assistance, ice strengthened hull and follow icebreaking channels, power according to class. And we had independent tankers, double acting tankers that go both ways, bow and equal strengthening bow and stern, power based on performance. this is just to illustrate the sizes of those vessels. In the conventional tankers were kind of between 18.5 to 21 megawatts, and the Azimuth tankers were 14.5 to 22 megawatts, and all the vessels were over 200 meters long, and these prices were 20 years ago, so I don't have any idea how much they would be today. And the result was such that going both ways, east and west, conventional type of vessel, 90,000 tonner, had about 1.9 to 2 US dollar per barrel, and the Azimuth vessel had 1.8 US dollar per barrel. But those vessels had not been built as such, but then there were two different projects that were launched in the early 2000s, and we had in the left we have the Varanday tanker that is carrying out the crude oil from Varanday, and on the right side we have a Preoslomnoja tanker that is taking oil from Preoslomnoja platform. They look a little bit different, and one is more double acting because it has a better open water, the Preoslomnoja one, and the Varanday one has been ensured that it can go in well in ice in both directions. So all these systems have been built. And now we are back in the already to the starting point that there are ships for real icebreakers. We have a bow propeller in the Azimuth in the bow propellers and two Azimuth in bow propellers, and so it's just that what is next. Thank you.
Thank you, Göran. This was a good overview of the different developments on icebreakers and the overall design requirements for Arctic vessels. Göran, please stay tuned for Q&A session at the end of the webinar.
Okay.
And as the next part of today's webinar, it's my pleasure now to give the floor to Sampo Viheriälehto from ABB Marine and Ports. Sampo, over to you then.
Okay, hello everybody, and nice to see so many people on board. Let's have a look at some operation practices, but because the topic said best practices, we have to broaden the scope just a little bit away from just how the ship are handled. Now here's a pretty picture, lots of icebreaker doing its thing, and the ship behind. Now perhaps the icebreaker guy might have wanted to keep the vessel just a tad closer here in the open. As it happened just a few minutes after this picture, the vessel was stuck. But this is just to the point that icebreaking really is a sport of wisdom after the fact. All right, let's have a look at the second. So before we go into the operation practices, icebreaking, they come in many different forms, like Göran said before. And just through an example, I want to highlight some things like the operational requirements are different for different icebreakers. Time or speed, for that matter, is a good example here. If you take the offshore ship, offshore operation might be that they are standing still, possibly in DP for most of the time, whereas you go to a seismic operation, seen here on the top right corner, you can't stop at all because the seismic vessel streamer will go down. And then again, if you go to a science operation, time in most cases don't play such a role in terms that you absolutely have to be somewhere at one particular time. And if you take a look at the line ice breaking side of it, it's fair to say that it's a constant hurry to get things done as fast as possible. Now, a little bit about the strategic planning side. I'd say that icebreaking really it starts long before the ship ever departs the port. So The first thing is to take a look at, of course, the operational area where you're going, and then have a look at the operational and navigational safety aspects to the whole thing. Now, what kind of equipment you're going to have on board, what kind of satellite image support, if not, perhaps even you might have a chopper with you to drop some satellite buoys down on the big features or not. So really, I'd say that the operational or strategic planning of the operations, that's the first step if you want to be able to mitigate the risks in the operation itself. So the strategic planning, of course, you have to take a look at the prevailing conditions, meaning mostly weather, like Göran said. If you're going high latitudes, as often is the case, either it's pitch black or it's the sun won't go down at all. So, and of course, the ice conditions, it might be a compressed first-year ice phenomena like here and the picture here below, but it also might be quite substantial multi-year ice features moving about. So all of those you have to take into account. Now, of course, you have to also take care of the sort of permitting issues. If it's going to be expected to have marine mammals, are you going to need marine mammal observers? If the operation is done by a normal shipping company, perhaps you will need ice pilots on board and all of that. So the maturity of the ship owner in ice condition is a crucial factor. So what we have then as a strategic side? Well, the aids to navigation on site probably might be there or not. As you can see, this buoy here is still in place, but you can see that the ice flow has moved around it. But oftentimes the ice buoys and aids to navigation get destroyed under ice or whatever. But also it's the level and quality of the data and equipment available. Many northern and southern far reach areas don't really have such great nautical chart coverage at all. What kind of satellite data you will be getting? And those are the things that you have to mitigate in one way or another. If you're unable to get one system, then you need something else to cover for it. So then we go to the tactical side. Now, as it often happens in icebreaking, is that you find yourself in a completely different situation as you first planned for. This may be many reasons to it. Sometimes the satellite images does not work with the reality. Oftentimes, as you go along in your operations, you will absolutely start to get a feeling as to how the satellite images differ from the operations itself. Here you can actually see quite a hairy situation on the lower picture. When the vessel got stuck behind the icebreaker, we only were a few minutes away, and in those few minutes of time, the ice was already climbing on board the vessel. So extreme ice pressure present. So here, the upper picture, also quite a thing to see in a nice pressure ice field. This very large vessel and in ballast conditions, I would say it's not optimal situation neither for towing or assisting. So how did we end up in a situation like that? So it all comes down to operational flexibility. So you must be able to read what's happening, and if it's easy, is it hard? And of course, sometimes it's better in line icebreaking to just wait for a few moments to help. Here's a nice picture on the lower right-hand side about the pilot boarding an assisted vessel. So optimum case is to drive the icebreaker as close here to the ice edge as possible so that the guys on the sleigh can climb on board the vessel. But of course you have to take good care not to exactly drive over the fellows because they will be standing right at the ice edge. And of course the limits of the icebreaker and assisted vessel, that's very important factor. Something that must be kept in mind all the time, how you assist different kinds of vessels and what kind of icebreaker you are using. And then in line icebreaking, it's always the traffic situation. Now, a couple of examples. The traffic situation is constantly, of course, monitored in many ways, but sometimes you will have congestion happening, and lots of vessels get beset at the same time. So who gets to be assisted first, who gets the second place, and how the queuing overall works. And those are, again, questions to the sort of operational side and operational flexibility. Needless to say that the fellow with the high ice pressure and dangerous situation, she must be assisted first. And then you got possibly the vessels quite close to each other, stuck, how the ice field is moving. If the ice field is relaxed, okay, the guys can wait for a few hours. But in any case, the guys who are pretty relaxed enough far away and in a nice line, they will certainly then get the assisting last. All right, let's take a little look on the maneuvering side of things. Here you can see to the point how the azimuth thrust helps in ice when you can push the main engine power sideways if needed. And on the right hand, the conventional ice breaking. In this picture, actually they are not notch towing, but quite so, like a really short cable towing, and sometimes that's also done without the cable. So I've got a few examples here on how the Azipod will help you in the traditional line ice breaking operations. So firstly, as it happens, you're moving in a convoy and the vessel behind you gets stuck. So the traditional thing to do is that you will reverse your icebreaker and then punch out of the track and move really, really close astern along the ship side as long as the ice cracks. Now that's fine, then you will accelerate and slowly pick her up. But the problem or inherent thing is that with the shaft line propulsion, it's firstly really difficult to punch out from the track when the ice is heavy. But also to do that you need momentum, and that means some speed. So you have to be close and moving astern at the same time, having a higher speed. So the problem here is that your bow will not be under control, and that is a significant risk of having the touching the beset vessel's bow. Now you mitigate that, of course, with keeping your movements and everything as good as you can under control. But in any case, in some ice conditions, it's quite difficult indeed. Now, with the Azipod, what you actually can do is that when you reverse your icebreaker and come out from the track, it will climb away quite nicely, and that is that you can use the icebreaker propulsion to pull you out from the track with the full main engine power. And when you're cutting the vessels loose, you can keep more safe distance and just slide by and push the Azipod sideways. We call it the flushing effect. And this is also very handy when you have more than one vessel behind you. So you can go ahead and reverse the icebreaker along the whole line of beset vessels, flush them out, and then continue again. So the bow control issue is something that in these kind of operations is very important. Bear in mind now that you are unable to use the conventional bow thrusters because they will suck in the ice, and that's not good for the bow thruster. But the Azipod, of course, is free of that problem. And then the conventional cutting beset vessels free. So the classic cut vessel loose situation. How it's done with shaft line, you inch your way close to the vessel and cut right in front of her, and usually even use your main engines reverse a bit, and then see if you can get her moving. Now, oftentimes this is done with high speed, close quarter, high risk. Whereas with Azipodpropulsion, you can again keep more distance, come slower, flush with the Azipods, flush the ice loose, and get going. You will also be having a wider free area at the ship's bow when you have passed her. And finally, we have the classic track in convoy operations side of things. In shaft line operations, like in the beginning we discussed shortly, the problem is when there's pressure in the ice field that the track will close. Sometimes it will close in 30 seconds. Other times it may stay open for a few hours or longer, but that's a rare case. Now, the icebreaker tends to leave a track that is as wide as the icebreaker is, and there's not much more you can do to make the track wider. So that means you have to keep the vessel closer. And there is the inherent line icebreaking risk, that if you want to make sure that the vessel can keep up with you, you have to keep her really close and increase the risk in case you come to a sudden stop yourself. Now with the Azipod propulsion, what you can do again is spread the track, and the track stays open longer, which means that firstly the vessel in assistance, it's easier for her to follow you, but also that you can keep a greater distance to her. So that always increases or decreases the risk and increases the operational efficiency. All right. So with that, let's wrap it up with a few bullets here, comparing the Azipod thrust to the shaft line icebreakers. So I'd say firstly the safety, the greater distance you can keep to the vessel in assistance by still being able to continue, the better. And close quarter operations when needed, they can be in better control because you can use the main engine vector wherever you like. And of course the efficiency in assisting because of the better performance, but also the flushing of cutting vessels free. But also you can assist the vessels with wider beam because you can spread the track, and the notch towing is not so often needed. And of course it's the operational envelope that you also broaden, because you can continue normal assistance in cases where the wind and ice pressure or ice pressure created by the wind would normally close the track so fast that the vessels can't keep up with you. But with the Azipod, you are spreading the track, you are just able to do it in harder conditions. All right, thanks on my part, and we'll see if any Q&A comes up later.
Thank you, Sampo. That was a good overview covering the operational requirements and ice navigation, ice breaking assistance tactics. And before moving out to the, and Sampo, please stay tuned for the Q&A session at the end of the presentation. And before moving to our final part and Q&A, I would like to speak briefly about the latest solution of ice-breaking ship propulsion. And for the equipment manufacturer and for the propulsion system, there are typical design requirements for the icebreaking vessels, like the overload capacity. It can be a continuous or periodical. There is a high torque requirement at the low propeller RPM, very high power requirement, and the machinery system has to have a fast dynamic response. On the operation, of course, there is a heavy load variation, which cause an increased wear of the machinery. The additional maintenance due to the wear and tear, and of course the power requirements are higher fuel consumption. So here are listed some ABB Technology contribution for icebreaking ship. Of course, our flagship product is the Azipodpropulsion that enables the new way of operate an icebreaking vessel. Electric propulsion provides the torque and the fast dynamical performance. I will cover a little bit about the propulsion control ice mode system we developed particularly for the LNG fueled icebreaking vessels. Energy storage is one possibility to have a faster dynamic performance and fuel savings. Onboard DC grid and the variable speed engines can provide a good benefits on improved performance and fuel savings. And then is the digital solutions like situational awareness, pilot vision, and the remote diagnostic systems. Our flagship product is Azipod, and actually this year we have 30 years when the first unit was delivered for icebreaking vessel. And today we have some 18 million operation hours on icebreaking vessels, and the highest ice class delivered is PC2, and in the track record is about 90 icebreakers or ice-going vessels. The Azipod products, we have a different product family with different letters, and for the icebreaking application we have two families, Azipod Ice for the lower power application from 2 to 5 megawatt with permanent magnet motor directly cooled to the seawater, and the units are available to PC3 ice classes. For the higher power application, we have units from 6 to 17 megawatt with the synchronous machines, and so far the highest ice classes have been PC2. Sampo explained about the operation principles of the vessel with the 3 Azipod units, 1 in the bow, 2 in the aft, and here are just some pictures of the ice trials from this icebreaker Polaris, and showing the unique maneuvering and turning capabilities in ice. With this Polaris concept, we just concluded a case study where we were looking at the battery hybrid solution on icebreakers, how that would enhance the operation and the ship economy. So we simulated a real operation load profile of an icebreaker and studied different battery applications. The conclusion from the case study was that the battery energy storage can provide enhanced environmental footprint by fuel savings up to 15%, reducing the CO2 emissions to some up to 16%, and methane emission up to 37%. Additional benefits of the load banks is the improved vessel performance and the faster load ramps and some additional redundancy. Also looking at the operational cost with the battery hybrid solution, the generator running hours can be reduced up to 46%. I mentioned that the other solutions have been these variable speed engine that the diesels can run always at the favorable operation point. And for these solutions, we have ABB have developed the onboard DC grid system, and for the higher power application, we have a dynamic AC. And these have been well tested in icebreaking vessel, onboard DC grid on the low voltage system with the power range up to 20 megawatt, the DC distribution, and the dynamic AC on the medium voltage system with the higher power application. One very famous project on the LNG transportation in the Arctic is the Yamal LNG carriers, 15 vessels with 3 15 megawatt Azipod units. And for that particular project was develop an ice mode propulsion control system. And the idea of the ice mode propulsion control function was to develop the system that to deal with the fast load variation in the propulsion and the power plant network. And the idea is that it's designed to minimize the load variation of LNG engines by utilizing the load banks and additionally the available power reserve in other electric propulsion motor. This is a real-life example of the ice mode functionality in heavy ice operation. There is a time on the horizontal axis and the power on the vertical axis. And this illustrates the case where two Azipod are experiencing a sudden load decrease. At the same time, the load banks kicks in immediately and stabilizing the overall power in the network. Other important aspect, design aspect on an icebreaker is the overload capacity of the propulsion system. There are of course different technologies, but the benefit of the electric propulsion is the over torque capacity, so that the propulsion motor and drive can provide immediate over torque capacity to keep the propeller running even in a heavy ice load, and additionally keeping the power plant stable. We have also other technologies, the marine pilot vision available, giving an additional view and giving a view at even at the darkness. Also, the remote diagnostic services are well utilized in icebreaking vessels, so that basically even operating in harsh remote conditions, you have a virtual engineer on board. A couple of years ago, we developed together with the company Aker Arctic a universal polar icebreaker concept, where we look into modern technology, dynamic AC propulsion concept, and the biggest or the largest Azipod unit available. And we were looking at a universal icebreaker with the 217 megawatt Azipod and this dynamic AC varying RPM engine configuration, icebreaking capability up to 2.4 meter, and we worked together with ABS Classification Society on the classification requirement principles for these Azipod units. So these were some of the technologies available: energy storage, dual fuel electric propulsion, digital solutions, variable speed generators, Azipod, and the propulsion control ice mode. So these are some of the elements that ABB have for the modern icebreaker. Universal icebreaker is not yet realized, but the one project that is currently coming in operation in the near future is a Ponant Icebreaker-expedition vessel with ice class PC2 with a lot of these functionalities and solutions. So I will conclude my part of the presentation about the technologies available for icebreakers. And this year we are celebrating the 30 years of the Azipod experience operating in ice conditions, and it has been proven to safe and energy efficient solution for several type of icebreaking vessels. And modern technologies and digital solutions, remote support and monitoring are one of the key elements and developments in order to support the operation in remote areas. And with that, we would like to proceed to Q&A session. And we have received some questions from the audience, and thank you everyone for your questions. So let me check. The first question would go to Göran. Göran, are you there?
Yeah, I'm here.
Yeah, so this is to Göran. Thank you, Göran, for sharing your knowledge. Are there specific design and operational challenges for vessels with combination of bow and stern Azipod units? For example, with vibration and noise, synchronization control, or global stress on the hull?
Yeah, that's a tough question. I have not been on board on such a vessel yet, but if you look at the old times when we had conventional shaft lines and propellers in the bow, those were not very human friendly, and there was a lot of vibration due to that. But now then we have Azipods, and at the vibrational level, even what we have seen before running astern, it's lower than conventional, and that's more or less like the bow itself, or hull strength is not the problem. It's more or less that we have to have the Azipod unit or whatever unit there is in the bow strong enough. That is basically we don't want to lose anything. And now I would say that I don't see any problems there.
Thanks. The next question to Sampo.
Okay, shoot.
So what is the operation strategy of an icebreaker with port propulsion in multi-year ice? Do you see a difference with the operation in the first year ice?
Well, I'd say the multi-year ice condition is somewhat same for any operation is ice, that is to avoid any extreme maneuvers, meaning that take the speed down before you make contact with the multi-year filter. And what we found economical to do was that just before you're hitting it, a few meters before, you will hit more power. Then you are in an accelerating ramp when you finally, on a few seconds, when you hit the flow. So you get the full power going. But I'd say that multi-year ice is such a potential danger to any ship moving at fast speed that always approach with caution. the Azipod is similar to any propeller in ice, that as long as the propeller is running, there is no risk from the ice contact. And to that point, actually, we've never lost an Azipod blade in ice conditions.
Thanks, Sampo. Next to Göran about the nuclear propulsion. So concerning nuclear propulsion for polar class vessel, like using a small modular reactors, do you think this solution will become industrially mainstream over the next, let's say, 10 to 20 years?
Nuclear, okay, all these nuclear things are very popular in the military navy vessels, and only vessels with nuclear propulsion have been in the Russian icebreakers operating far in the north. And it's very handy because you only come to refuel in every 5 years, but there's always the problem with the reactor itself. Of course, the nuclear reactor technology has also advanced, and it could be possible because it doesn't make any other waste than the human waste in sailing. But commercially general, I don't think so. It could be only in Russia.
Thanks. Sampo. So we are talking about the importance of Azipod. I mean, our presentation was Azipod for icebreakers. What about these assisted vessels? Do they need an Azipod or they don't need an Azipod?
Well, certainly it would help, because the idea in icebreaking or line icebreaking is that the vessels must move by themselves as long as they can, unless there's a special reason for the icebreakers to just call them to please stop. But yes, of course, if you have an Azipod-equipped vessel, you can reverse your vessel and go stern first in the tough ice as long as you can. And if it finally is more than your engine power or thrust can handle, then certainly you can flush yourself free, or create yourself a nice little pond to wait for the icebreaker. So certainly it would help in maneuvering, but also that you can make it further away without the need of an icebreaker.
Okay, and then a question about we presented a universal polar icebreaker concept, and there was a question that that does not include an Azipod on the bow, but the bow thruster. Why not include an Azipod on the bow also? Well, this is something we discussed, and we have been discussing that this vessel was particularly designed to operate in a heavy multi-year ice, and we don't see a beneficial. It's a risk to operate a bow thruster in a heavy multi-year ice. That's why it was designed that it has a heavy icebreaking bow and more power on the aft. Do you, Sampo, have any comments on this?
Yeah, it's a nice example of balancing your operational requirements and the ship you're designing. So if the only idea is that you go in midst of the heaviest possible multi-year ice, and the conventional wisdom is on the side that, okay, keep the bow without thrusters. But if you are in any kind of mixed or first-year ice condition, having to do efficient icebreaking work, having requirements for excellent maneuverability, then opt for the bow unit. So it again begins with the idea of where you are going to take your vessel to, into what kind of conditions, and take it from there.
All right. So one more question to Göran. So the presentation was about the design requirements for the Arctic ships. icebreaking Arctic ship. So how do you see that these icebreaker design requirements for Arctic vessel differs those from operating in Antarctic?
No, they are not so much different, but normally when you go to Antarctica, it's more like a ship sailing alone, very little assisted operation, and ice is somewhat different. The salinity of water is a little bit different, and the ice is moving in a different way. The Antarctica, around the continent, there is a current that moves ice back and forth, or actually goes one way, and there is nothing commercial going on, and it's not allowed to be, and there's no oil activity, there's nothing like that, and it's more like individual ships. Some cargo ships go assisted, and the vessels can be, let's say, in a operational way more simple, in that way you don't really need bow propellers, or you can have just aft propellers when you are going basically straight lines. The only thing is that most of those ships that go to Antarctica, they are also research vessels, and they have DEP, and they have all that possibility to do research in the area, and that then may require some extra elements in that. But if you look at what is in the Arctic, we have more commercial traffic, at least on the eastern part, and that means that you have to be able to go from one place to another. You have to be able to assist those ships that are not so good in. So that's a little bit different philosophy altogether.
Right. Good. Thank you, Göran, and thank you all. We have now come to the end of today's ABB Tech Talk session. Very many thanks to Göran Wilkman and Sampo Viheriälehto for sharing your insight and experience about icebreaking technologies and operation. Tomorrow we will have another Tech Talks about the underwater noise by Mr. Tomi Veikonheimo and Janne Roivainen. So please join that one. And thank you everyone for participating in today's webinar, and we look forward to welcoming you again at the upcoming ABB Tech Talk session for the marine industry. Thank you very much.
Thank you, everybody.
Thank you.